here with us. It's the very last seminar of the course. We thought the last one was the last one, but no. It's kind of complicated time because now all the students are in examination period. But yeah, I'm super happy to have Professor Fulvio with us. Professor Fulvio is a world-leading expert in robust multi-hazard analysis of the structures. I'm very happy because we met for the first time in the print project that we have right now. And the idea is super groundbreaking. The idea is to assess the condition of populations of structures. As you know now, the big challenge is not the isolated structure, but the populations of a structure. We know how to do SHM of one single structure, but the big challenge is what happens when we have thousands of different structures, like bridges, which is the topic of today. The achievements of Professor Fulvio are just huge. Let me just give you a quick overview of his CV. Professor Fulvio is an associate professor of structural engineering and coordinator of the master program in forensic engineering at the University of Naples, Federico II, in Italy. As I said, he's an expert in multi-hazard and risk assessment of structures, authoring more than 200 papers. He's editor of Construction and Building Materials, which is a super top journal in our field. He's member of many different organizations for standardization, research entities. So basically, we have a big expert today with us. So I'm super happy to give you the stage. Thanks a lot.
Thank you. Thank you very much. Thank you very much for your kind invitation, first of all, hosting, and also the introduction of today's seminar. Okay. So I'm very happy to be here. This is the first time for me in the Universidad de Granada. So very much appreciated. Today we will talk about how we are advancing in the hazard assessment. Probably we should switch off some microphones. So somebody.
Tutto bene, la vedo domani.
Perfect. Okay, and so we will talk about how we are integrating multi-scale computational simulations with experimental testing in order to inform with each other our tools. So first of all, I would like to introduce you about our research framework at the RISE Lab of University of Naples, Federico II. These are a short list of the main topics we are dealing with in Naples in order to provide the best of our information and knowledge to all the stakeholders regarding civil infrastructure, particularly for existing highway bridges, and hence to foster multi-hazard engineering or delivering some, I would say, optimal solutions for both design and I would say more critical is the assessment side for this critical infrastructure in order to provide solutions for more safety and I would say also sustainability of our disaster risk management. So here we will focus on multi-hazard risk assessment, but also with the integration of numerical simulation and experimental testing. This is a list of our latest research projects regarding civil infrastructure. And this is the first one is the project mentioned before by Professor Garcia Macias. So fail safe. Actually, we are now shifting from the paradigm of fail safe to safe to fail. So this is our challenging objective of next future, I would say. We obviously collaborate with several companies. You will see which are the outcomes of this cooperation, particularly for the management of existing infrastructure. And so this is the outline of this talk. We will first of all talk about laws. Why? Because we have to access the variability of the input loads to our infrastructure, and this is why, based on wave motion system, we are now assessing a lot of data. So I would say, first of all, collecting a lot of data and then analyzing them in order to support structural health monitoring, but also structural assessment of particularly of bridges, of existing bridges. So we will also move across structural capacity assessment, both from the experimental and numerical sides, and then we will end up with some vulnerability and risk exercises, or I would say studies, regarding roadway bridges. Finally, ending with the presentation with the robustness assessment. So first of all, we collected a lot of data regarding wind systems. This is not only to support structural health monitoring, but also in view of facility managers to support the assessment of traffic overloading, because one of the most recurrent criticalities for the management of our bridges is the presence of overloading, which in many cases has also produced the collapse of some bridges, particularly in Italy, but also in other parts of Europe. We also used the WIM data in order to develop some models, I would say probabilistic models, for vulnerability and risk assessment of existing bridges. And so we selected some case study bridges in order to collect data, and starting with this rationale behind this system. The system were initially installed by facility managers in order to deviate some exceptional vehicles. So in one case, we may have a negative wind check where we are able to assess the exceedance of some thresholds which meet safety requirements of the bridges, particularly. And in this case, we are able to deviate heavy vehicles. In other cases, okay, we have a positive check, so the traffic is allowed on the civil infrastructure. Please take a look at this control panel, because we are able to collect data about some significant parameters of the traffic loads. So one is the acceleration, but also I would say the vehicle size, and also the axle load and speed of each vehicle. So we are able to characterize each vehicle. I would say also with a photograph, with a picture of the vehicle itself, but this is directly a matter of policy, so not a matter of structural engineering. The outline of this first study is this one, where we have a threefold assessment and simulation procedure of the study. We initially collected data in order to access the level of traffic, so accessing the parameters that I mentioned before. In part 2 of the study, we performed a statistical assessment of the data, and then we developed a simulation procedure which allow you to simulate a set of vehicles running over, for instance, a bridge or any other part of the transport infrastructure. So we selected 2 wind stations. Why? Because in this first wind station, which is called Fratte, we were able to enforce some restriction of gross vehicle weight to 40 tons. So more or less with a 10% error with respect to or around, say, tolerance with respect to 44 tons, which are the safety threshold of our, at least in Italy, guidelines, okay, for the traffic. And so based on this condition, we also selected another wind station, which is here called Ponte Cagnano. It is far away from Salerno, which is southeast of Naples. And then in this case, there was no enforcement of the maximum gross vehicle weight. So we were able also to access the differences with respect to some conditions where we are able to deviate, for instance, heavy vehicles and with respect to the others. In part one, we accessed the traffic data. This is, for instance, the outcome of our clustering of low weight and heavy weight vehicles. So we were able to record in 2 weeks, particularly, in order to access also variations with respect to several days of the week, but also with respect to several conditions, working days, for instance, with respect to the others. And then we compared the traffic data with respect to other wind stations in Europe. So, for instance, if you give a look at the Igualada station in Spain, we have more or less the same conditions with respect to Ponte Cagnano in Fratte, which are Italian wind stations. So more or less 500 or 600 as kilonewtons for the maximum gross vehicle weight. Then we accessed the traffic flows. Wind stations provides you good data in order to differentiate between several traffic conditions with respect to free flow, following flow, but also traffic jams. In this case, for instance, you can see here a traffic jam, okay, with respect to a 24-hour time window. Then we clustered the data with respect to different vehicle classes. Why? Because based on the previously mentioned control panel of the wind stations, we were able to classify each vehicle. So for each vehicle, we were able to identify the class of the vehicle, and then we performed a statistical analysis in order to access the frequency of occurrence of each class. For instance, you can see the most recurrent vehicle classes 2A, 4D, and also 5F in red. And also with respect to the gross vehicle weight in Ponte Cagnano, but also in Fratte, okay? So we accessed the gross vehicle weight in terms of average value and also the speed for each class. As you can see here, the problem is this, I would say, very small figure in terms of frequency of occurrence, more or less 2% of PV weight vehicles. This is the worst condition for the, I would say, the bridges. So very rare events for the bridges, but if they happen, they can produce catastrophic consequences of the bridge. So this is why we talk about also the robustness of the bridges regarding extreme events. So in part 2 of the study, we analyzed statistically all the data. And then we grouped all the data in order to fit several probability distributions. In most cases, we find multimodal distributions, so a mixture of distributions in order to simulate at our best the different load conditions on the bridges. Then this is, for instance, an example for class 5F vehicles, which is one of the most recurrent ones, as I said before. In this case, we were able to develop the different probability distributions. For instance, here you can see in dashed lines a two-modal, a bimodal distribution. Okay, so in many cases we were able to visualize several modes for our distributions. Then we performed this type of analysis for each of the main features of the WIM datasets. So this is the case of Excel weight, but another very important parameter was the time headway in order to best, or I would say better simulate the traffic over our infrastructure, and then avoiding overlapping between different vehicles when they transit over a bridge, I would say. Then in the final part of the study, we developed and validated a simulation procedure in order to ideally simulate vehicles running over a bridge. Okay, so based on the previously mentioned probability distributions, we simulated the vehicles transit over a bridge in order to access okay, in this case, for instance, the different weight conditions on the bridge itself, and then simulating the different traffic conditions. Here you can see free flow, following flow, and traffic jam. Okay. Then we validated the procedure for each class from 2A to 7I. And then we compared the recorded versus the simulated data sets in order to develop some probabilistic models that can be used for vulnerability assessment, but also to be coupled with, I would say, some SHM systems. Okay, and then performing an input informed SHM of civil infrastructure. But this was the first part of the study, because then we carried out a set of 15 laboratory tests on concrete bridge builders in order to inform at our best the structural models that we will discuss afterwards. Goal number one was to evaluate the effects of different gravity conditions, because in many cases, particularly in case of post-tensioned concrete builders, we identify some partial or even lacking grouting for the tendons. This may be a vulnerability factor for the bridge itself, because you perfectly know that the presence of air, but also water infiltration within the tendons can produce corrosion. And we will see also what can happen in case of corrosion of the bridge. Then this is the experimental setup. We performed a 4-point bending test in order to simulate the presence of a tandem load. So one of the vehicle traffic load models for the bridge. We reduced the scale of the bridge itself. So starting from a prototype with a span length of approximately 30 meters. Then we reduced the scale to 1.5, 1 to 5, and then we reduced the length to approximately 6 meters. Okay, so we simulated one of the most recurrent study schemes for bridge decks, which is the simply supported one. And then we also simulated the presence of the tendons. So in this case, 2 monostrand tendons within the concrete builders that were post-tensioned. So before testing, we pre-stressed the steel within the tendons. These are some pictures regarding construction and pretesting phases. All the strands were also equipped with strain gauges in order to monitor the level of pre-stress together with some load cells at the end sections of each specimen. Then we defined two loading protocols. Why? Because we would like to produce some knowledge with respect to two main conditions for the bridge: safe visibility, but also collapse capacity. And this is why we defined the protocol number one, which is more or less oriented to a conventional safety check for the bridge. Then simulating three peak loads, one regarding safe visibility limit states, so SLE. The other one is regarding the ultimate limit state, and finally we also scaled of 5%, 50%, sorry, the ultimate limit state conventional load. So we got three peaks in our protocol loading number one, and then afterwards we started the protocol number two, which is related to monotonic loading in collapse of each of the 15 girders. What about the impact of lack of grouting? In this case, this may have a strong effect, for instance, on SHM systems, because we have a huge flexibility. So, if we, for instance, make SHM in terms of frequency variation, so we develop some control charts in terms of frequency variations, and then defining anomalies in terms of frequency. This may be a case, a warning case, because we have very large deflections of the concrete girder. And so this may be a problem for sensitivity assessment, because according to guidelines delivered by the American Concrete Institute, so ACI, the ACI guidelines provide us with some indices, so some indicators. One of the most important indicators is the index of deviation from linear behavior. In this case, we are able to access the variations in terms, I would say, so as a proxy of stiffness reduction, as the loading, the level of loading progressively increases over the bridge. And so in this case, we are able to, with respect to thresholds of more or less 25%, we are able to visualize conditions that exceed these thresholds in terms of serviceability. And this was the case of specimens with partially grouted or even ungrouted technodes. But what about the collapse capacity? In this case, we can see that particularly in case of partial grouting, we don't have significant sensitivity with respect to the ultimate load, while in case of the lack of grouting at some locations of the girders, we may have a 12 to 15% reduction, so loss of ultimate capacity. So this may be the case of ultimate limit state safety checks. Then we also made some cross comparisons on the upper part of the slide on the left side, on the right side, sorry. You can see the different locations for our specimens in terms of lack of grouting within the tendons. So in one case, we simulated partial grouting around the mid cross section of the girders. This is just half of the girders because there were some symmetric conditions for the girders. While in other two specimens, we simulated lateral partial grouting. Okay, so we had an asymmetric condition of grouting for the girders. Please keep in mind this statement because we will see also the consequences of this asymmetric condition for the girders. But also we made some analytical studies in order to further expand our knowledge with respect to different effects of partial grouting, but also initial pre-stress level. And so here you can see that according also to this simplified, I would say, formulation, we can state that cracking load, so serviceability, depends also on the initial level of pre-stress. This is opposite, obviously, to the case of ultimate pre-stress conditions. When we don't have, we lose, I would say, the sensitivity with respect to the initial pre-stress. So we should be more aware of the condition, I would say, degradation of the girders with respect to the loss of initial pre-stress, or I would say the loss of pre-stress within the tendons with respect to ultimate mistake safety checks. We also performed the classical fractional analysis, okay, particularly in case of cracking and ultimately mistakes. We here in green lines, we can see that the model error was very low. So this is good because according to a very simplified analysis of the cross section, we are able to more or less have an indication about the safety, both at cracking and also ultimately mistake. Goal number 2 was also the evaluation of the effects of strain rupture, because in many cases, due to not only corrosion, but also if you look at the case of bridge overpasses, you may have some impact of vehicles over the edge bridge. And so in this case, you may have, as a consequence of the impact, some local damage to the bridge. In this case, we may have also a strain rupture, which produces, or may produce, I would say, brittle failure for the bridge girder. Why? Because we have a transfer and migration of stresses on the upper part of the cross section, and then we have an overstressing of the concrete slab. So in this case, we are able to see concrete crushing in the upper part of the cross section. About the cyclic response, obviously local damage produces higher flexibility, while particularly in case of ultimately state conditions, we have a huge capacity loss. This is important because we previously stated that the lack of grouting may not produce significant capacity losses with respect to this case. So in the previous one, we were able to see more or less 15%, okay, of capacity loss. In this case, we are now seeing that this capacity loss may even approximately reaches 40%. So from 15% to 40%. Very huge. More or less irrespective of the level of pre-stress again. So 38% to versus 37, more or less the same. And this was the impact of, if you look at the second picture of the overall bridge builder, the effect of local damage. We would expect the ultimate living state condition at the mid section of the builder. But what about not only the demand, the bending demand, but if we look at the maximum demand to capacity ratio, capacity reduces significantly here due to strain rupture, and then there is a migration, a translation of the section where we have the maximum demand to capacity ratio. This is why we have rupture not at the midspan where we apply the traffic load, but more or less at the location of the strain rupture. So we have an asymmetric collapse condition for the builder. And based on this benchmark experimental program, we then carried out some numerical simulation. Okay, this is the case, for instance, of nonlinear finite element simulation within Abacus. In this case, we simulated two conditions, so bonded versus unbonded tendons, and then simulating the pre-stress force according to Savrulati et al., which allow us to define a thermal distortion. So we directly applied a thermal distortion to the bridge builder in order to indirectly, I would say implicitly, simulate the tendon pre-stress within the model of the builder. Okay, we performed obviously a material modeling according to the CDP model, and hence according to this formulation that you probably know with respect to tensile and compressive damage parameters, which allow us to control the level of damage with respect to each material of the model. Then we validated our model with respect to the experimental force displacement curves. So here you can see the comparison between the simulations and the and testing, I would say. Here you can also see in green lines the outcomes in terms of model error. So if you are interested in doing some probabilistic assessment, here you can also include in your simulation the model error with respect to the reality. So in our case, the experimentation. And here, I don't know if, okay, yes, it works. Here you can see as we proceed on with the force displacement level, we are able to visualize what happens in terms of damage. So in this case, concrete crushing at the location of the midspan, so between the loading section, with a distributed tensile damage. The same more or less occurs in case of partially bonded tendons. But here you can see more interaction also with respect to the steel wraps, so mild steel reinforcement within the girder. While in case of unbonded tendons, you can see a strong difference in terms of the shape of the force displacement curve, with also a difference in terms of damage, both in tension and compression, because here you can see some concentration of tensile damage here with respect to the previous cases, but also concentration of concrete crushing at the location of the loaded section. This is the simulated versus the observed damage, but I would like to stress this condition, okay? So based on what I mentioned before, in case of local damage in the girders, we are able to simulate different rotations at the end sections. And this may have some effects also in terms of operational model analysis, so ACGM again. We then simulated some corrosion effects. According to Franceschini et al., so a simplified model where we are able to simulate the degradation of material properties with respect to, I would say, fitting corrosion. Then we calibrated, first of all, the interbehavior, and then we simulated different corrosion severity levels. So we defined three corrosion levels: minor, moderate, and severe. Minor corrosion may even happen in many cases. Okay, you can observe this type of corrosion. And then we simulated different locations and extents of corrosion with respect to the gross length of the girders. So between 50% and even 100% of the span, of the total span length of the girders. In this case, you can see that there may be some strong differences in terms of load bearing capacity. So we may even have a load bearing capacity loss of between 10 and 20% with respect to moderate corrosion, while observing even approximately 40% of loss in case of severe corrosion. So this reflects the fact that severe corrosion may have more or less the same effects of strength rupture. Okay, we previously saw that the presence of local damage in the form of strength rupture may even produce 40% loss of load bearing capacity. This is more or less the same figure in case of severe corrosion. These are the simulations, animations, I would say, of force displacement and also damage in the girders. We have a strong variability in terms of force displacement diagram, with even pre-yielding premature collapse of the girder in case of severe corrosion, so CR3, the maximum one. Then we performed a multi-level assessment with several computational approaches, not only finite element modeling, but also applied element modeling, in order to assess the possible benefits of the different computational procedures with respect to computational time. Why? Because particularly in case of a huge number of simulations in probabilistic modeling, we have to reduce the computational time for each analysis. And so this was the case because in case of applied element modeling, we reduced the computational time from 1 hour in Abacus to 5 minutes. And the difference in terms of different orders of magnitude progressively increases with respect to the size of the model. So this was the case of a single hill. But what about the case of a huge bridge deck? Okay, so this may be strongly important for us to speed up our computations, and this, however, is the case of the same accuracy, I would say, between finite element modeling and applied element modeling, with in this case, in this latter case, also the possibility, if you look at the dashed line, to reproduce also the force capacity drop as deflection progressively increases. We can also, and this is very good, we can also simulate what happens within each tendon. So in terms of ultimate capacity assessment, you should think about the effects of large displacements. So geometric nonlinearity. Geometric nonlinearity plays a key role in this case because we have a catenary action within the cables, so within the tendons, and this is a source of progressive increase in terms of pre-stress level within the tendons. So starting from the initial condition, we progressively visualize the increase in the level of pre-stress. And then we simulated the case of entire bridge decks, also according to several construction practice rules. So simulating, for instance, different conditions of connection or lacking connection between the cross girders and the slab. This may have some role with respect to redistribution capacity after local damage. Here you can see the case of higher redistribution capacity when we have RC cross girders connected to the slab. Okay, so in this case, you can see, for instance, here, tendency to some fracture line, here, but also there. So we have a more distributed damage and cooperation between several bridge components of the deck. We even simulated the case of pre-stressed cross girders. In this case, we get the maximum capacity. If you look at these lines, the black line is the case of pre-stressed cross girders. So we have the maximization of redistribution capacity. The dashed line in red, simulates the level of demand on each girder according to a simplified Fulvio and Gesser analysis. And then we simulated all these things in order to support the vulnerability assessment. How? By means of a mechanics-based fragility analysis under traffic laws. So the measure of our fragility curves, the intensity measure, was assumed to be the level of traffic loading over the deck. This was the typical cross-section that we analyzed. And then, according to our previously collected data on material properties, we implemented all these things in terms of probabilistic modeling within our fragility analysis procedure in order to simulate different conditions for the deck. This is the input in terms of uncertainty modeling for our analysis. So simulating variability in material properties, geometric properties, but also the loads. These are the plots, for instance, regarding probability distributions of girder length, but also pre-stressing steel strength and so on. Hence, according to a simplified component Gesser analysis, which was motivated by the possibility of running this type of analysis over a huge number of bridges, okay? We then computed our fragility points with respect to this alpha parameter. And alpha parameter is the ratio between the intensity of the traffic load with respect to the design level. So Q sub D is the design level of the tandem load on the bridge deck. Okay, so we have a normalized intensity measure, a dimensionless, say, intensity measure in this case. So alpha equal to unity is the case of design loads over the bridge deck. In many cases, we identified some failure with respect to bending, while just in 1% of cases we identified some shear failure of the deck. Then we implemented also the new traffic load models within our procedure. So I would say new traffic load models according to Italian guidelines for existing bridges. If you look at, for instance, the EV load ratio 44 tons that I mentioned before, this is quite lower with respect to 60 tons of the Unicode load model number 1. So this may be quite good in order to better manage the safety of existing infrastructure. So the level of maximum loading over the bridge deck was reduced with respect to Eurocode 1. But what about the consequences, the benefits, I would say, of some actions decided by facility managers? In many cases, they decide to reduce the number of traffic lanes in order to, however, have a trade-off between safety but also operational level of the bridge, so transitability of the bridge itself. And what about the effects in terms of vulnerability? Because they are anthropic loads on the bridge. So we are able to also reduce not only the vulnerability, but also the hazard itself. Okay, opposite to the case of natural hazards, obviously. And so in this case, we defined the different fragility curves for 3, 2, and even 1 traffic lane. Okay, then progressively increasing the ordinates of these diagrams. And this is reflected also by the reduction, the progressive reduction in terms of probability of failure, because here you can see that, for instance, if you consider alpha equal to 1, so under design loads, the probability of failure reduces from 6 by 10 to minus 3 to even 8 by 10 to minus 4. So 1 order of magnitude. This is very good, obviously, for the reliability against traffic loads. And what about also the effects of another vulnerability reduction measure, which may be the increase in the distance between the traffic lanes and the curb, where the most stressed beam is located. What about the effects in terms of vulnerability? Obviously, also in this case, we simulated these different traffic conditions on the bridge deck, and then accessing the increase in the capacity of the bridge, and hence the reduction in terms of fragility against traffic loads. In any case, here NTC stands for Norme Tecniche per le Costruzioni, so the Italian building code. And here you can see that regardless of the distance of the traffic lane x sub 0 with respect to the curb, regardless of this fact, we in any case have fragility curves with respect to NTC higher, okay, with respect to Italian guidelines. This is an obvious consequence of the fact that we reduce the peak load from the 60 tons to 44. And then we implemented all these things into a novel software, QBridge software. We are at the stage of submission for a paper about this software, which will be, however, available to everyone on the website of the LUIS, which is the Italian network for structural engineering and earthquake engineering laboratories. But what about the inclusion of all the hazards together in order to have optimal solutions for risk reduction? Because we discussed the effects of, I would say, the condition of the bridge with respect to grouting, strength rupture, and so on, with respect to traffic laws. But what about the other hazards? Earthquake, fire, so not only natural but also anthropic hazards. Italian guidelines provide us a very good approach, but this approach is based on qualitative assessment. So it is not based on some indicators of the risk. Okay, so in this case, we, according to this flowchart, first of all, have a census of the bridges over the Italian territory. Then we perform some visual inspections, and then we are able to assess the condition of each bridge, and then we progressively are able to identify what is the level of priority for the bridges. The problem is that in many cases, based on these guidelines, we also have many conditions for high priority of bridges. This is by definition according to the qualitative approach. So here, for instance, for structural degradation, seismic, landslide, and hydraulic risk, we are able to define a priority class for each of them, then combining all of them into a single multi-hazard class, but considering these type of hazards. What about anthropic hazards? They are not, at the moment, they are not considered. This is why we formulated a holistic approach, but based on some indicators, in order to perform, first of all, a territorial scale assessment, and then prioritizing the high-risk bridges, so safety critical bridges, for more detailed assessment. In our first study, we considered these hazards, so gravity loads, earthquakes, vehicle impact, and fire. Also combining the information with the condition of the bridge. According to existing literature, we defined the level of risk with respect to traffic and seismic hazards, so combining them into a single priority class according to the average, either the average or critical component condition level. So according to UK guidelines for bridge condition index. And then we took into account the level of fire risk according to existing literature, okay? And the same was made for vehicle impact risk. In any case, we visualized all the components of the risk. So moving from the hazard, then crossing vulnerability, and then ending with the exposure. But most of novelty was, I would say, relied in the proposal of multi-hazard risk indicators. So we combined all the risk sources into a single indicator in order to better prioritize interventions or more detailed assessment of the bridge, according to several decision-making related factors, which are these weighting factors for each single single hazard assessment. So each risk indicator was weighted by a coefficient which may be obviously defined according to decision makers. The several combinations of the weighting factors and conditions for the bridge provided us with the 5 indicators. Okay, 5 indicators, particularly if you look at the latest ones, based on these weighting factors. The first one was related to gravity loads and conditions, so this is why we assigned it equal to unity, because it is the most important one. Then it is followed by the weighting factor for the earthquake hazards, and then moving to the other hazards considered in the study, so fire, risk, and variable impact. We then implemented this procedure over an initial stock of 30 highway bridges located in the north of Italy. In this case, we consider it as an indicator of the traffic, not the wind data sets, because we were in parallel progressively collecting and analyzing those data, but based on the average daily traffic. Average daily traffic is a common measure used by facility managers, but the problem is that also in this case, there may be a saturation of the high-risk class of the bridges. Why? Because we have an average daily traffic that exceeds the maximum level defined by the Italian guidelines. This may be an additional problem with respect to the overall problem that we are managing. Please look at the fact that in more than 80% of cases, we identified simply supported study schemes. So this is why we also selected this kind of study scheme for the experimentation in our laboratory. Then we identified, modeled and also propagated the uncertainties by means of design of experiments, and hence this is why we collected a huge number of these kind of plots with respect to the variability of each multi-hazard indicator. So in this case, for instance, you can see on the right hand side of the slide the case of the fourth multi-hazard risk index, where we, for each bridge, were able to access the variability of this index according to the information that we have. Okay, so before visual inspections, we may first of all carry out, I would say, a desk analysis, and then after the visual inspections, we are able to inform the procedure and hence to account for them in the final output of the multi-hazard risk index. So with respect to the previous case, if you look at the variability of the box plot, here we have huge variability. Why? Because the condition of each bridge is not the same. So there may be a strong impact of visual inspections with respect to our computations. Here you can see also different sensitivity levels of each indicators, and this is why we selected the fourth indicator among the 5 indicators that we proposed, because it is more sensitive to the information. And higher sensitivity is reflected by higher level of coefficient of variation in terms of statistical analysis. Okay, and here you are able then to see the effects of this procedure and this information with respect to classification of each bridge. So we defined 5 classes. this is according also to the Italian guidelines for existing bridges, but in the first instance, we defined some fixed thresholds in order to identify the several classes. The problem is the limitation of this approach, because we were not able to access some high priority but also low priority bridges. We have no figures in this case in the table. We have a concentration of our simulation output in the middle part of the distribution. This is also the case of another ranking, which is not based on the mean value of the risk indicator, but on the upper tail value. If mu stands for the mean value, mu plus 2 sigma is the statistics with respect to the upper tail of the distribution. But what about the possibility of redefining these thresholds for the risk classes as statistically based? If we look at the variability of the multi-risk indicators, then we are able to define the distribution, the overall distribution of the multi-hazard risk index over all the bridge portfolio. In this case, we are able to access the thresholds in statistical terms. This turns out to be an infrastructure-specific assessment, okay, for the bridge portfolio. And then we are able to populate also the high priority, but also the low priority classes of the bridge portfolio. Then improving our classification of bridges in order to improve prioritization and hence management. This is the case of procedure number 1, where we accounted for all the variabilities in the properties of the bridges. But a more practice-oriented approach, procedure number 2, was based on the assessment of each bridge deterministically. So obviously, if you look at the practice by facility managers, they are not able to run the millions of simulations as in the previous case. So for each bridge, you are able to have a single figure, a single number. But again, if you look at huge bridge portfolios, you have a variability again of the multi-hazard risk indicator. So again, you are able to visualize this distribution, and again, you are able to define or redefine your thresholds for prioritization. The problem is that if you use the more accurate approach, so procedure number 1, you are able to visualize in black which are distinctly the bridges that are actually in the high risk class. While in the case of procedure number 2, this is not possible in some cases. This is reflected by this comparison. If you look at here on the right hand side, the lower part of the slide, here, okay, you are able to visualize high priority bridges according to procedure number 1, but this is not the case of procedure number 2. You apparently would have 0 bridges in this class. So you may have an underestimation of the priority level of the bridges. And what about the comparison with respect to Italian guidelines? Again, Italian guidelines would result at the moment into a possible saturation of the high risk class. This is not the case of our procedure when you have a distribution of, in any case, a distribution of the bridge. Why? Because the distribution of the multi-hazard risk indicator is adaptive. It's able to adapt itself with respect to each single infrastructure that you are managing. So this is not possible. This is by definition a situation that is not possible according to this procedure. The further developments are the inclusion of hydrogeological risk. We are now processing the data with respect to landslide risk, always according to existing methods, but according to our holistic procedure. Hydraulic risk also accounting for scour. This is the case. And then we are now redefining our ranking for the bridges, also including the hydrogeological risk. So in this case, ending up with an overall picture about the risk, but with respect to all possible hazards that can threaten our bridge portfolios. And then the final part of this presentation is related to robustness, because of some local damage due to scour, for instance. In many cases, we are able to visualize some propagation of failure starting from obviously the scoured part of the bridge, then moving upward to the deck. And in many cases, it even ends with the collapse, as was observed in this case, which was the Rubianello Bridge in northern Italy, which collapsed after a huge flooding event. We modeled the bridge again according to a CDP modeling approach, hence considering different mechanical properties. I have no time to go more in depth in this study, but I will provide you also with additional information if you want through some papers. And then we also accounting for different levels of traffic loading. According to the previously mentioned new traffic load models, so according to Italian guidelines, we simulated the heavy, medium, or light traffic loading conditions over the bridge. And also different positions of the traffic loading moving over the bridge. Okay? And then we simulated through, I would say, cohesive elements and the removal of cohesive elements at the base of one pier, the level of scour. So P by B was assumed to be an intensity measure for the scour level. And starting by 6%, then getting 50% of scoured section, this section. And then we accessing the distributions of equivalent plastic strains within the model, which could be also correlated with some other proxies of the structural behavior. For instance, even the crack width in the model itself. This is a plot of the evolution of plastic strains according to an increasing level of scour. And then we assessed the bridge robustness in terms of also displacement, so downward displacement of the bridge at different locations of the bridge, so piers, but also arches, foundations, abutments, and so on. According to the different locations of the traffic load with respect to each of those bridge components that could be obviously monitored through an SHL system again, then we are able to access which are the maximum effects. And obviously, we confirmed the fact that if we install an SHM system over a pier, then the worst condition is to have the traffic load at a location between 0 and 1/4 of the length of the arch length of the bridge. While if we have a central loading condition with respect to the arch, we maximize the effects of the arch itself. Then we are able to have this, I would say, another type of control chart, which is related to the displacement level, the downward displacement level of the scoured pier of the masonry arch bridge under increasing level of scouring. So we are able to define some thresholds after which the displacement may have divergence due to a near collapse condition for the bridge. Then we could in further developments integrate this kind of model-based output with some, I would say, more data-driven approaches, for instance, with respect to the input of traffic loading. So not only based on the conventional traffic load models, but on the actual level of traffic over the bridge, according to wind stations, so wind measurements. And then I would like to end this presentation inviting all of you and disseminating information with respect to robustness, but robustness school with respect to the second edition of an international summer school at the University of Naples, which will be held at the end, actually, of this summer. So from 13th of September to 3rd of October, all of you are invited. The main lecturers are this one, apart from me, Professor Jose Adam, Professor Beck, Professor Caspini, and Professor Itzulin. Also including a hybrid session with respect to specific topics which may have some interaction with respect to robustness. We will also visit all our experimental facilities, and also an important thing is the fact that we will merge theoretical lectures with exercise classes in order to simulate understanding by the audience. The topics at the glance are this one, also moving across reliability and risk-based approaches again, and then ending up also with some applications regarding experimental testing in collapse with some SHM applications to prevent progressive collapse. Okay, with the medal, so a championship also with respect to certification of participation. I would like also to thank all our supporting institutions with respect to funding of this or supporting of this support to this initiative. And so all information is available on the internet, on the website of the event. The deadline for registration is 15 July, so please look at this possibility, and thank you for your kind attention.
I think it was a very round talk. So you started from characterization of loads, combining everything into a holistic approach. I think for many of you can be interesting. I think about it. So I think especially for me, that's going to be very helpful. Do you have any questions? Somebody from the audience?
Thank you, Professor, for this interesting presentation. Actually, I had curiosity about the generating of the fragility curve because it's a multi-hazard assessment. So I wanted to know it's analytical one or no, and what is the engineering demand parameter for that?
Yes. We in that case we computed the traffic load trajectory. So it was not multi-hazard, but considering also the condition of the bridge, okay, but just with respect to traffic loads. Okay, this may be an ingredient, an information, I would say, for one of the components of the multi-hazard risk indicators I discussed before. And this was completely mechanics-based, so analytic, based on simplified component gas analysis for bending and shear demand over the edge bridge, the edge giver of the bridge deck. And about the engineering demand parameter, yes, I showed it before that we considered the traffic load on the first lane of our model.
And the other question that I had is about the combination of the loads. For example, earthquake, and for example, there was tower, and considering all of these effects on the bridge, I wanted to know, you don't think it's so qualitative? Because, for example, if we change the layout of the bridge, everything can be changed. For example, the height of the piers, or the number of spans. So,
You mean in the multi-hazard
Yes.
risk assessment?
Yeah.
The procedure that I showed before.
yes.
Yeah. Actually, we have no chance to combine the loads because we carry out a single risk assessment. Okay, so for each hazard itself, and then we combine the risk indicators, not the loads. Okay. It is not a mechanics-based approach. However, obviously, yeah, I agree with you on the fact that there may be some bias in the combination. So of loads, but okay, this may open the way to some, I would say, scenario-based analysis. Other than you have some information regarding the traffic loads and the combination with respect to your infrastructure. In that case, you might also consider some conventional combinations provided by guidelines, standards, codes, and so on. In this case, you might consider, for instance, provisions by Eurocode 1 in order to combine effectively the different types of loads according to some semi-probabilistic format of the loads. In some cases, like it is a very rare case, I also noticed some, I would say, probabilistic assessments of the assets. So in that case, if you select a time window, for instance, 1 year, 15 years, and so on, you might be able to characterize all the hazards over the same time window. But it is quite challenging, particularly for consideration of extreme events.
Yeah, actually, I have a similar concern. If it's possible to take into account the probability of having different effects combined in the same period of time, I imagine it's challenging.
Yeah. Yeah, in this case, which is more strictly related to robustness assessment of the bridges, or I would say progressive collapse risk assessment. In this case, we typically combine the hazards in terms of scenarios, and then previously selecting what we assume the worst conditions for the bridge, so the worst combinations, and given each of those scenarios, we perform a probability scanner. So starting from this, I would say, deterministic combination.
Question?
First of all, thank you for the presentation. Was interesting, especially the fact of finding a clinical way to identify the condition of bridges. rather than at 5 levels of the new guidelines. I was just curious about the first part of the lecture. First of all, I was curious about the model of the girder in Naples. You said that you modeled the pre-stress condition with a different temperature. I believe that's with a defined field in Naples. So I was curious if you applied, if you studied on pre-stress girder with pre-tension rather than post-tension in that case. No, or maybe you found a way to adapt that kind of technique to post-tension girder.
Well, in line of principle, you could also use this procedure for pre-stress, so pre-tension. Okay. However, we were not able to do that because of the sake of time, but we might have further.
Okay, thank you. The second one, I saw that you related the condition of the girder in the laboratory girder to the pre-stress level of the tendons. In your opinion, what do you think it would be to export this information to real case in real case grid? Since in Italy we have a lot of simple supported post-tension girders without knowing the level of pre-stress. So, what do you think? What is your picture?
Yeah, thank you for this interesting question. This is why we combine the experimental testing with the numerical testing, so numerical simulation, in order to access the different sensitivity of cracking, peak load capacity, and so on, the deflection capacity with respect to the initial pre-stress level. We even in one study considered the variability of the pressure, so a probabilistic variability, statistical uncertainty with respect to the level of pre-stress in the girders. But in any case, this level of pre-stress does not produce a significant influence on the ultimate load capacity. In terms of serviceability, we also observed significant outcomes. This strongly and further supports motivations behind the use of ACGM systems. So a combined use of ACGM systems with all these type of tools. Thank you so much. You're welcome.
Any other question? I just have one small curiosity. It's about the attention classes of the guidelines.
Yeah.
Do you think it's necessary to study the uncertainty behind this? Because from my point of view, it's quite uncertain, and the impact of defining high level of risk or medium level of risk basically raw, and it depends on very quantitative aspects. I don't know if you're.
Yes, there is a lot of subjectivity, obviously in this type of procedure. But I would also like to stress the different motivations of the direct guidelines, because we should have a trade-off between the safety at national level and the supervision of the country, the state, government agencies, and so on, and the safety management of each facility management company. Our procedure was primarily based on the second way, okay, of looking at the problem. About the safety level and national level, there may be some problems. So, okay, to use more quantitative risk indicators, but the problem is that the level of thresholds should be, at least ideally, based on a uniform knowledge over the entire bridge stock of the country. So that is the main problem. So One good condition could be, but there is some progress with respect to this issue, is to collect data with respect to reaching a uniform level of information across all the country. So based on this, some national security agencies, for instance, we have SPISA in Italy, could inform their procedure in order to define a more statistically based threshold sets for multi-risk indicators. And then this might reduce the level of subjectivity, at least in the ranking of the breaches. Probably subjectivity will remain, however, for each single breach. This may be a problem also related to the fact of the different interpretations of the guidelines by different facility managers. So there may be some problem. But there is also, I would like to say, a training process with respect to additional level, with respect to the technicians of facility management. So also the level of information and the ability to use this procedure is improving. So this may further reduce subjectivity behind the risk assessment.
Thank you. Thanks a lot. Any further questions? So we thanks again our speaker. Thanks a lot. Bye guys, those who are online. See you next time. Bye bye.
See you.
Excuse
Bye.
me.
Bye.
Excuse me.
Sorry,
Can
there is
you
a,
hear me?
yeah,
Yes,
sure.
I have a question, and also there was another guy who had a question, but now he's not here. Excuse me. I would like to ask you something briefly. If you can say to me how you determine the coefficient of exposure in the slide, where you spoke about the vulnerability, the exposure, and the hazard. I think it was like the 73 slide, something like this.
Yes. Slide 70. Okay.
I can see there is the exposure.
Here?
I cannot see because you are not sharing the screen.
Yes. You mean this one?
Okay, yeah, this one. Where is exposure E equal 0.3 multiply
Yes.
heat is this one.
Yes, this is related. This is. I can provide you also the paper regarding this approach. This was a literature-based approach. However, in this case, we are able to see different components. So E sub TT to ERC, which are able to provide us with respect to different exposure level to traffic loads, but also considering the level of, I would say, exposure to each kind of hazard. So in this case, not only traffic load, but also seismic hazard. So this is this provides you with a complete level of information with respect to different exposure components.
Okay, can you share the paper or the name of the paper where I can find the information
Yes.
about
If you
coefficient,
send-
please?
We have no no connection with respect to the paper here because I have no I have not the PDF file, but I can send you. If you can send me an email, I can provide you the information, specific information about this.
Okay, perfect. So
Okay.
thank you. I will search the email.
Yeah. Perfect. Thank you very much.
Thank you. Bye bye.
You're welcome. Bye bye.